So let's look at a different curve. Let's look at 1 minus x squared. So that is a parabola that opens down, that is vertically shifted up 1. And we're going to look between 0 and 1. So here's our little shaded blue area. We're calling it R this time. Now we could look at a right-hand sum or a left-hand sum, and this time the right-hand sums, because the curve was decreasing, are going to underestimate our actual area, and you can see the left-hand sums are going to overestimate. But we could still use this same idea. We see that the little widths are 0.25 or 1/4, and then the height of this would be putting in the interval ends here from the right hand side, or the other one from the left hand side, into the function, getting a value and doing length times width and summing them up. So if we looked at the right hand sum, we would get that each of the little widths is 1/4, and if we took that 1/4 and we did 1 minus 1/4 squared, we would get our 15/16 times our 1/4. And then if we do the same thing here with 1/2, here is our next rectangle, here is our next rectangle, and then our last rectangle is 0 high, and we sum those up and we would get 0.53125, which we know underestimates because these pieces are missing. If we looked at the left-hand sum and we started by putting in here, we can see if we put in 0, we would have this 1/4 wide, and putting a 0 in here, it would be 1 high, and so we could sum those up and we would get approximately 0.78125, and again, we're not exact and we would have overestimated this time. Now what if we did the middle? If the left does one thing, either over or underestimate, depending on if our curve's increasing or decreasing, and if the right does the other, well, why not pick somewhere in the middle? So we could actually do a midpoint. We could pick a halfway point to use for the height of our rectangle. Now, the width of our rectangle is still 1/4 on each of these, but now if we went right in the middle and figured out that value in the middle, which would be 1/8, and put that in the function and got out a y value there, you can see that we underestimated for this part and overestimated for this part, and they tend to kind of cancel each other out a little more. Now they're not exactly the same, the under and over estimate, so it's still going to be an approximate, but that's going to be better than always overestimating or always underestimating. So you can see here we would be under by this but over by that, and under by this but over by that. In this particular case, with what this curve is doing, this is going to be more accurate. So as we compute those values, we would have 0.671875, which is a value between what we got when we did the left-hand sum and what we got when we did the right-hand sum. Here's a table so you can get an idea and kind of see how they compare for this curve. So we have n being the number of rectangles. We could do a right-hand sum, a left-hand sum, or right here in the middle is this midpoint. And you can see that as we started this here, that we know that this one was way under, this one was way over, and this one was somewhere in between. But notice as we go to 1,000 rectangles, how these values, whether we use left, right, or middle, if we get enough rectangles, they are all approaching the same value. The limit as n goes to infinity of a left-hand sum, a midpoint sum, or a right-hand sum would all equal each other, and in this case it looks like they are approaching 0.6666, which is 2/3, based on looking at a table trying to estimate what the limit is. So we're going to take any curve, and if we would like to know the area under the curve, we are going to divide this into intervals. Now, what would be the width of each interval? Well, if n was the number of rectangles, our width for each of these would be b minus a, because that would give us the total length here, and then divided by the number of rectangles. So we call our little width delta x, that just means the difference in the x, and it's going to be b minus a divided by n. So after we get the width of our intervals, which would be delta x, that would be the little width of our rectangles, we would need to decide what our height would be. And we would need to decide, are we going to do left-hand sum, right-hand sum, midpoint? In this particular one, we've got a right endpoint. And as we would sum those up, then we would have the function value at x sub 1, because that's the right hand side of the first interval, times by the little width of the rectangle, delta x, plus then to get the second rectangle right here, we would have the function value at x sub 2, and then that would be the height, and we'd multiply that by how wide it is, delta x, and so forth. So just looking here, we could have n equal 2, and whatever the curve was, you can see that if we were using these right endpoints that I overestimated and I underestimated and then I way underestimated. If we look at n equal 4, because the curve both increases and decreases, you can see sometimes we overestimate, sometimes we underestimate. I could look at n equal 8. I'm getting more accurate. I have less areas where I over and underestimate. So as we sum these up, the more rectangles we can sum up, the more accuracy. And you can see we're doing even better. But what if, as we do this, instead of picking the right side, the left side, or the middle, what if we just randomly picked somewhere on the interval? And we could do that as well. So this is just showing these little dashed blue lines. We just picked somewhere on the interval, went and found the function value, and drew a rectangle there. So sometimes we overestimate, sometimes we underestimate, but we could just do that as well. So whichever we choose, we know the limit as the number of rectangles goes to infinity is going to approach the actual area. So this is just to kind of summarize. If we had this region that lies under the graph of a continuous function, then the limit of the sum of the areas of the approximating rectangles as n approaches infinity will give us the area. So if we could let n go to infinity, it doesn't matter what we use for the x value on this interval. It could be left, right, middle, or something random. And if we let n go to infinity, it is going to equal the area. One last thing, remind you about sigma notation, because this can be helpful as we're writing the sums of all of these rectangles. So if I had something like this, if we remember, this number tells us what integer to start with in creating the terms of a sequence. So if we were adding up rectangles here, likely we would start with 1 here. And then this number tells us when to stop. In this case, the last integer would be whatever's up here. And then this over here is the formula we substituted into. And for adding up rectangles, that formula is going to be the height of the rectangle, which is going to be the function value at some x on the interval, multiplied by the width of the rectangle, which is going to be delta x. And remember, this is a capital sigma, and it means to sum up or add up each of the terms in the sequence. So we're going to be approximating areas under curves by using what are called Riemann sums, and this is named after a German mathematician, Bernhard Riemann. And even though the idea of integration was formulated in the 17th century, it wasn't until almost 200 years later that Riemann came along and developed the underlying mathematical theory for integration. So he lived from 1826 to 1866, and here's our idea of our Riemann sum. Now this particular one is divided into even partitions, but instead of using a left hand, right hand, or midpoint sum, here's an example where we just do the random pick sums. And Riemann didn't always evenly partition either. He often worked with various widths. Now it makes sense to do an even width for simplicity, so we can use the summation notation, so we can save ourselves a lot of calculations. But we don't have to use left, right, middle, or random. There could be other schemes as well, which we will look at in just a minute. But the big idea then is we can get the area of a region under a curve of a continuous function if we're looking from A to B by these approximating rectangles, and then we could let the number of rectangles go to infinity and we would have the area. Now using the summation notation, first of all we've got the approximate, and we can use this summation notation, which means we are going to be summing up from 1 to n rectangles, and we're using this value on each of the intervals. And then if we let the number of rectangles go to infinity, here it is in summation notation, then instead of an approximate area we have the exact area. So last thing, let's just think about a couple other schemes for summing these up, and I'm just going to end by talking about a couple of those. So we could have what would be called an upper sum, and what we would do to get this upper sum is we would partition this into, we'll do it into 4 intervals here, and then we would look on this first interval and see the uppermost value or the greatest function value on that interval, and it looks like it happens to be the endpoint. Then we would look on the second interval, and this one happens to be on the right endpoint, the uppermost or greatest function value on that interval. Now let's go ahead and look on this third interval, and it looks like the right endpoint is the greatest function value on that interval. And then looking on this last interval, it looks like the greatest or uppermost function value on that interval is right about there. So it's the value of the function on that interval, not its position. Similarly, we could do a lower sum, and we would do the same idea, but we would be looking for the lowest function value. So on this first interval, we would see the lowest value for the function, and we would make the rectangle that high. And then we would do the same thing on this next interval. We would look for the lowest function value on the interval, and that's where we would make the rectangle. And then on the third interval, same thing, we look for the lowest, and that's where we would make the rectangle. And then on the last one, we would do the same thing, the lowest function value on that interval. Area of these four rectangles would be an approximation for the area under the curve using the lower sum.